Imagine for a second. Imagine you are tasked with guaranteeing that a massive, immensely powerful nuclear power plant will never melt down.
Right, even during some completely freak accident.
Exactly. Even if multiple redundant systems fail simultaneously, you obviously can't just, trigger a real loss of coolant accident to test your theoretical safety margins.
No, that would be a terrible idea.
Yeah, so instead you have to build this incredibly complex virtual matrix to predict the unpredictable, down to the microsecond and the millimeter. Welcome to today's Deep Dive.
Be glad to be here.
Today we are unpacking exactly how structural and thermal hydraulic engineers actually pull off this monumental computational feat. We're looking at a highly detailed set of mechanical engineering lecture slides from Dr. Belal Almomani.
Yes, from the King Fahd University of Petroleum and Minerals.
Right, specifically this is material from course ME 507, term 252.
And this material offers a really rare look under the hood of nuclear safety architecture. The mission for our deep dive today is to demystify the rigorous world of nuclear reactor core thermal hydraulic system analysis.
Which is quite a title.
It is a mouthful, but we're going to unpack the specific architecture of the computer codes used to simulate these transient accidents, explore the surprisingly dangerous physics of boiling water, and understand the limits of these mathematical safety nets.
Because it's really about taking extreme, chaotic physical phenomena and trying to bind them into controllable zeta.
Precisely. Translating the physical into the digital.
The idea of mathematically bounding a disaster to prevent it in physical reality is just a fascinating engineering challenge. So let's start with the foundational safety assessment frameworks from the slides. How do engineers structurally approach the safety profile of a reactor before they even write a single line of code?
Well, they rely heavily on two distinct but really complementary methodologies. The first is deterministic safety analysis, or DSA, and the second is probabilistic safety analysis, PSA.
Okay, let's break those down for the listener. Deterministic safety analysis is highly structured, right? It's very rigid.
Very rigid. It looks at postulated events. So an engineer models a specific initiator, like, say, a double-ended guillotine brake in a primary coolant pipe.
And DSA doesn't care at all about the statistical likelihood of that pipe actually breaking.
Not at all. It just assumes the break occurs instantly. Then it applies a strict, predetermined set of rules to see if the plant's safety systems can prevent a breach of the containment boundaries based on really strict acceptance criteria.
Like ensuring that peak cladding temperature never exceeds a regulatory limit, right?
Yeah.
I think the slides mentioned something like 1204 degrees Celsius.
Exactly. That rigid structure is the defining characteristic of DSA. It functions as an absolute stress test. Probabilistic safety analysis, on the other hand, focuses entirely on the statistical risk matrix.
So PSA combines the likelihood of those initiating events happening in the first place,
along with the probability of safety system failures and their ultimate consequences, to estimate the overall risk. This is where you calculate metrics like core damage frequency.
Or large early release frequency, right? It gives you a holistic statistical picture of the plant's vulnerability.
Exactly. It highlights which specific component failures contribute the most to the overall risk.
Here's where it gets really interesting, though. Looking at the slides, there's a massive historical paradigm shift happening in how these specific assessments are conducted.
Yes, particularly the deterministic ones.
Historically, the industry relied on these overly conservative models, focusing strictly on design basis accidents. But the modern trend is shifting aggressively toward best estimate models with uncertainty quantification.
And that transition is arguably the most significant analytical shift in the industry's history. Under the old conservative models, engineers were required to assume the absolute worst-case scenario for every single variable simultaneously.
Like assuming the highest possible decay heat generation.
Right, and the worst possible power peaking factors inside the core, plus the absolute minimum performance from the emergency core cooling systems.
Which mathematically guarantees safety on paper, sure. But practically, stacking extreme worst-case scenarios on top of each other creates a physical model that doesn't actually represent reality at all.
It skews the data entirely.
If you design a system to handle an artificially exaggerated, impossible scenario, you might actually optimize the plant for the wrong physical transient,
making it perform less efficiently or even less safely under realistic accident conditions. That is the crucial flaw in over-conservatism. A best estimate model strips away those artificial mandated penalties.
So the codes are designed to simulate the physical phenomena as accurately as the physics engine allows.
Yes, but because no model is perfect, you couple that realistic simulation with a rigorous uncertainty quantification. You map out the exact statistical confidence intervals of your predictions.
And this shift is what allows engineers to tackle beyond design basis events and severe accidents, which means situations involving active core degradation.
Exactly. It gives us a much sharper, highly realistic analytical lens.
But to achieve that realistic lens, to simulate a severe accident without relying on artificial conservatism, engineers require immense computational firepower.
Which brings us to the thermal hydraulic codes, or TH codes.
Dr. Almomani's slides detail a whole hierarchy of these tools. You've got system codes, subchannel codes, CFD computational fluid dynamics for localized 3D phenomena, containment analysis codes, and severe accident codes.
And there are some legendary legacy code names in the slides too, like ReLA 53D, Cobra, and VPRE.
And to build this virtual representation of a reactor, these advanced codes rely on a highly sophisticated mathematical framework, the six-field equation model for two-phase flow.
The computational load of a six-field equation is just staggering.
Yeah.
When we talk about two-phase flow in a reactor, we are talking about water existing as a subcooled liquid and as a vapor steam simultaneously within the same control volume.
But the code can't just treat that mixture as a single homogeneous fluid, right?
No, it has to independently calculate the conservation of mass, momentum, and energy for the liquid phase, and then simultaneously calculate those exact same three parameters for the vapor phase.
It's a lot of math. Solving those 6 conservation equations concurrently across thousands of nodes is just the baseline.
Take the conservation of momentum, for example. The code has to calculate the physical force and velocity of the liquid phase moving through a pipe network,
while at the same time calculating the momentum of the vapor phase pushing through that exact same space.
Right. And if the vapor is moving faster than the liquid, which is typical, the code has to constantly calculate the interfacial drag.
The physical shear force and momentum transfer happening at the boundary between the water and the steam. It's not just tracking water flowing in a pipe.
Exactly. And if that interfacial drag calculation is off by even a fraction, the downstream consequences in the simulation are massive.
Because the code might miscalculate a pressure spike or fail to predict a severe water hammer effect that could actually rupture a valve in reality. The momentum vectors are completely intertwined.
They are entirely coupled. Furthermore, the complexity scales up because the codes have to track variables beyond just water and steam. They have to account for non-condensable gases like nitrogen or hydrogen,
which get grouped into the vapor phase calculation.
Yes. Concurrently, they must track dissolved solutes like boron within the liquid phase.
And tracking the dissolved boron is where the computational matrix becomes exceptionally unforgiving. Boron concentration dictates the reactivity of the core.
Right. The code has to track the exact flow path and concentration of that boron dynamically as it moves through the primary loop.
Because if the simulation loses track of the boron concentration in a specific node for even a fraction of a second, the coupled neutronic simulation will incorrectly calculate the core's power output,
rendering the entire transient analysis invalid. The precision required is immense. And the true proving ground for codes like ReLAP5-3D occurs at the microscopic boundary layer right on the surface of the nuclear fuel rods.
Okay, let's unpack this part. Because the physical phenomena modeled there dictate the survival of the entire core. Dr. Almomani details the ReLAP5-3D boiling and condensing curves.
Yes, which maps exactly how heat transfers from a superheated zircaloy fuel rod into the surrounding coolant. The optimal operational state is called nucleate boiling.
That's moving from point A to B on the curve, right? Where discrete vapor bubbles form at microscopic nucleation sites on the heated metal cladding.
Driven by buoyancy and fluid flow, those bubbles detach rapidly. This carries significant latent heat away from the rod, while subcooled liquid instantly rushes in to re-wet the surface.
It's a highly efficient, incredibly rapid cycle of heat transfer.
It is, but that efficiency has a strict thermodynamic limit. And this is the critical threshold in thermal hydraulics. The slides refer to it as departure from nucleate boiling, or DNB.
Also known as critical heat flux, CHF, or simply the boiling crisis. Reaching the boiling crisis is the exact scenario the safety systems are designed to prevent.
Because the danger of critical heat flux comes down to the stark difference in thermal conductivity between liquid water and vapor. If the heat flux pushes past the critical limit, the vapor bubbles generate so rapidly that they coalesce.
They physically can't detach fast enough, so instantly a continuous solid film of vapor envelops the entire surface of the fuel rod.
And the formation of that vapor film is catastrophic from a heat transfer perspective. Vapor is a terrible conductor of heat compared to liquid water, so that film acts as a powerful thermal insulator.
The moment the film forms, the heat transfer coefficient plummets. The decay heat continuously generated inside the fuel pellet suddenly hits a massive thermal resistance at the cladding boundary.
Because the heat cannot efficiently transfer across the vapor blanket into the bulk coolant, the thermal energy is trapped inside the rod.
Meaning the temperature of the circular cladding spikes violently, sometimes by hundreds of degrees in a matter of seconds. And if that isn't arrested immediately, you risk melting the cladding.
To prevent that, the simulation must predict the precise microsecond that vapor film will form. The slides outline the specific empirical correlations the codes use to map this physical reality.
And the mathematical rulebook actually changes depending on where the fluid is on the boiling curve.
Yes. For standard, highly efficient nucleate boiling, RELAP5 3D relies heavily on the Chen correlation.
Which is brilliant because it recognizes that nucleate boiling in a flowing system is actually two distinct mechanisms operating in tandem. It calculates the macroscopic convective heat transfer of the bulk fluid flowing past the rod.
And superimposes that with the microscopic heat transfer of the bubbles forming and detaching at the wall.
Giving you a highly accurate, continuous calculation of the heat leaving the fuel. But the Chen correlation breaks down as you approach the boiling crisis.
Right. To predict the exact onset of critical heat flux, the codes abandon pure analytical equations and switch to the Groeneveld, Chang, and Doan table lookup method.
Using a table lookup instead of a pure algorithmic equation is such a fascinating engineering compromise. The physics occurring at the exact split second of CHF are just so chaotic.
The localized fluid turbulence, the bubble coalescence, it's so highly nonlinear that analytical models consistently fail to predict them reliably across different pressures and flows.
The fluid dynamics simply become too chaotic for a neat equation.
Instead, the lookup tables are built from thousands of standardized, meticulously recorded empirical data points from physical experiments.
So the simulation looks at the current local pressure, mass flux, and thermodynamic quality in a specific node and pulls the critical heat flux value directly from the empirical database.
It provides a grounded, highly reliable trigger point for the simulation to recognize the crisis.
And if the transient pushes the system past that trigger point, the code must dynamically switch its physics engine again.
Yes, if the fluid enters the unstable region of transition boiling, the code utilizes the Chen-Sundaram-Oskainak correlation.
And if it degrades all the way into full film boiling, where that continuous vapor blanket is fully established, it relies on the modified Bromley correlation.
Bromley's correlation really highlights how extreme the physical environment becomes. The original work analyzed the Tiller instability of the vapor-liquid interface, but the modified Bromley correlation has to introduce an entirely new heat transfer mechanism.
Thermal radiation.
Exactly.
At those extreme temperatures, the metal is so hot it is radiating thermal energy directly across the vapor gap into the surrounding liquid.
The code has to actively calculate that radiative heat transfer, which is a massive computational pivot from the convective models used just seconds earlier in the simulation timeline.
It's a staggering orchestration of fluid mechanics and thermodynamics, which brings us to a necessary reality check regarding the virtual matrix itself. So what does this all mean? Are these codes perfect?
What's fascinating here is, no, they are not flawless. The fundamental limitation of any thermohydraulic code lies in the inherent uncertainties baked into the models themselves.
You have to trace the mathematics back to their origin. The vast majority of those complex equations and the empirical data for the correlations are derived from laboratory experiments.
And to gather clean data in a lab, researchers naturally establish steady-state, fully developed flow conditions. It isolates the variables and makes the math solvable.
But a nuclear accident is the absolute antithesis of steady state. It is violently transient, chaotic, flow rapidly reversing, pressure plummeting.
We are taking mathematics derived in a perfectly controlled environment and asking them to accurately predict the fluid dynamics of a hurricane.
Not to mention the massive scaling discrepancy. We physically test friction factors on small pipes in a lab, but apply them to nuclear plant pipes that are a meter in diameter.
The fluid flow regimes can shift dramatically when you scale the geometry up by orders of magnitude. Plus, the experimental data always has natural scatter.
Even in the most controlled lab, taking the same measurement twice yields slightly different results.
Right, microscopic measurement errors. That natural scatter means the baseline equations already possess a known band of uncertainty.
And even if we could resolve the scaling issues and eliminate data scatter, There's an inescapable structural limitation inherent to the software itself. The slides identify it as representation uncertainty or nodalization.
Yes, translating a physical 3D power plant into discrete digital blocks or nodes for a computer to read will always introduce a gap between the code and physical reality.
If your nodes are too large, the mathematical average completely glosses over highly localized physical phenomena, like a localized temperature spike on a single grid spacer.
But if you make the nodes too small, mapping the reactor down to the millimeter, the computational matrix becomes so massive that the simulation grinds to a halt. It might take months of supercomputer time for a 10-minute accident.
Rendering the tool useless for iterative safety analysis. So no matter how good the math is, a RELAP5 3D model will always be a slightly pixelated version of physical reality.
And that pixelation is why uncertainty quantification is now mandatory. Engineers running the analysis must maintain a deep respect for the limitations of the mathematics.
It really is a profound engineering discipline when you look at the entirety of it. We started with the transition from rigid deterministic rules to statistical reality, explored the punishing six-field equations, navigated the boiling crisis, and faced the limits of mathematical models.
All to validate the safety margins that allow nuclear energy to function as a viable, secure backbone of the power grid.
Exactly. This intense level of math is the invisible shield protecting the public and keeping the lights on safely.
It is the mathematical foundation of nuclear safety, and it leaves you pondering something as we push towards AI and infinitely faster computing.
Oh,
Will our digital nodalizations eventually become perfect atom-for-atom digital twins of these reactor cores? Or is the violent, chaotic nature of a multi-phase transient fundamentally unsimulatable at a deterministic level?
meaning we will always have to rely on a small, calculated leap of engineering faith. What a profound final thought regarding the limits of computational physics. Thank you so much for joining us for this deep dive. See you next time.